More than 50 kilometers beneath the English Channel lies one of the greatest engineering achievements in history. Every day, passenger trains, freight trains, and vehicle shuttles travel between Britain and mainland Europe as if this underground route had always existed. But just a few decades ago, most experts believed such a tunnel could never be built. Engineers faced an almost impossible challenge. They had to drill from opposite sides of the sea at the same time, deep beneath the ocean floor, while working through layers of rock under enormous pressure. Even the smallest mistake could flood the tunnel or cause both excavation teams to completely miss each other after traveling nearly 40 kilometers underground. Massive tunnel boring machines worked around the clock, but every meter they advanced made the project even more difficult. Extreme water pressure, mechanical failures, and rapidly rising costs pushed one of the 20th century's most ambitious construction projects to the edge of disaster. Today, we'll uncover how engineers built the seemingly impossible Channel Tunnel, why it nearly became one of history's most expensive failures, and how two construction teams managed to meet beneath the sea with astonishing precision.
The idea of connecting Britain and mainland Europe didn't begin in the modern age. In fact, the dream dates back hundreds of years. As early as 1751, French engineer Nicolas de Marest proposed building a tunnel beneath the English Channel. At the time, it sounded like pure fantasy. The technology simply didn't exist, and no construction materials could survive the crushing pressure beneath the sea. The idea resurfaced during the Napoleonic era. France imagined moving troops quickly into Britain, while Britain feared exactly that possibility. Political tensions and military concerns buried the proposal before construction could even begin. The first serious attempt came in 1880. A French company started digging an experimental tunnel using an early tunneling shield and successfully excavated nearly 2 kilometers beneath the seabed. For the first time, engineers proved that tunneling under the channel was technically possible. But Britain saw the tunnel as a potential invasion route. Under heavy political pressure, the project was shut down. Throughout the 20th century, several more attempts were launched. Exploratory tunnels were started, surveys were completed, and ambitious plans were announced. Yet every project collapsed because of political disagreements, financial problems, or changing governments. For more than 2 centuries, the Channel Tunnel remained one of engineering's greatest unfinished dreams.
Building a tunnel under the ocean wasn't simply a matter of digging straight ahead. The ground beneath the English Channel is made up of different layers of chalk, clay, and limestone that formed millions of years ago. Some layers were too soft and would collapse instantly. Others were so hard that excavation would become painfully slow and economically impossible. Engineers needed a geological layer that was both strong enough to support a tunnel and waterproof enough to keep the sea from pouring inside. After years of geological surveys and dozens of offshore drilling operations, they finally discovered the perfect solution. Roughly 40 meters below the seabed lay a thick layer of chalk marl, a unique mixture of chalk and clay. The clay sealed many of the natural pores, making the rock remarkably resistant to water, while the chalk remained soft enough for giant tunnel boring machines to cut through efficiently. Even better, this geological layer stretched continuously from France to England, with nearly the same thickness throughout the route. It was as if nature itself had already prepared a hidden corridor beneath the sea. But this perfect layer still contained dangerous faults and underground fractures.
Even after engineers proved the tunnel could be built, another obstacle remained: money. The estimated cost reached nearly £4.7 billion, equivalent to well over $15 billion today. It would become one of the largest privately funded infrastructure projects ever attempted. Banks hesitated to invest without government guarantees. At the same time, politicians on both sides of the channel argued endlessly over the project. Many British officials worried the tunnel could become an easy route for terrorists, illegal immigration, or even a future military invasion. French leaders, however, viewed it as an opportunity to strengthen trade and permanently connect Britain with continental Europe. After years of negotiations, both governments finally approved the plan in 1984 and launched an international competition. A private consortium called Eurotunnel won with a bold proposal. Instead of building a single tunnel, they would construct 3 parallel tunnels, 2 for railway traffic and a 3rd service tunnel dedicated to maintenance and emergency evacuations. In 1986, Britain and France officially signed the agreement, and construction on Europe's largest engineering project finally began. But the biggest financial challenges were only getting started.
To carve a tunnel beneath the sea, engineers built 11 enormous tunnel boring machines. Each machine stretched nearly the length of a football field and weighed well over 1,000 tons of crushed chalk every day. For its time, the progress was astonishing. Some machines advanced several dozen meters daily, while one British machine named Catherine achieved an incredible record by excavating more than 428 meters in a single week. But every meter came at a cost. The cutting tools wore out constantly. Every few hundred meters, workers had to stop the entire machine and replace damaged cutters inside specially pressurized chambers designed to keep seawater out. The work resembled conditions inside a spacecraft. Crews operated under high air pressure, wearing breathing equipment while racing against strict time limits before decompression became dangerous. Meanwhile, the excavated chalk turned into a thick, muddy slurry that was pumped back to the surface. Britain later used much of this material to create an artificial hill, while France used it to reinforce parts of its coastline. As construction accelerated from both countries, the world's attention shifted to one extraordinary question. Would the two teams actually meet beneath the sea, exactly where they were supposed to?
Construction crews launched the giant tunnel boring machines from both England and France at the same time. Their mission sounded almost impossible: travel nearly 40 kilometers underground and meet at exactly the same point beneath the English Channel. The finished design included 3 separate tunnels. 2 large railway tunnels, each measuring 7.6 meters in diameter, would carry trains in opposite directions. Between them, engineers built a smaller 4.8-meter service tunnel that would later become the project's safety lifeline. The real challenge wasn't simply digging. It was navigation. Deep underground, there were no GPS satellites, no visible landmarks, and no room for error. If either machine drifted even slightly off course, the tunnels could pass each other without ever connecting, destroying years of work and billions of dollars in investment. To prevent that nightmare, engineers relied on laser-guided gyroscopes, inertial navigation systems, and incredibly detailed mathematical models that constantly tracked every movement of the machines. Over nearly 40 kilometers of excavation, the allowable error was less than half a meter. At the time, it was one of the most precise underground navigation projects ever attempted.
Building the Channel Tunnel demanded far more than engineering brilliance. It required extraordinary endurance. Thousands of workers descended underground every day into an environment filled with deafening noise, constant vibration, high humidity, and complete darkness beyond the construction zone. The greatest danger was always water. Several times during construction, the boring machines broke into water-filled fractures hidden inside the rock. Pressurized seawater rushed toward the tunnel with enormous force, threatening to flood entire sections within minutes. Emergency watertight doors immediately sealed affected areas while crews evacuated to safety. These systems prevented disasters that could have claimed dozens of lives. Even without major accidents, the working conditions were brutal. Many workers developed hearing damage from the continuous roar of heavy machinery. Fine chalk dust filled the air, affecting their lungs, while constant vibration and damp conditions caused long-term joint and muscle problems. Despite the risks, the crews continued pushing forward every single day, knowing that stopping the project was never an option. Every meter they completed brought them closer to one historic moment.
On December 1st, 1990, history was made beneath the English Channel. After years of non-stop excavation, the British and French tunnel boring machines finally reached each other deep below the seabed. As the final layer of chalk disappeared, daylight didn't pour through.
Instead, a small opening appeared between two teams that had spent years working toward the same destination without ever seeing one another. British supervisor Graham Fagg and French supervisor Philippe Cosette reached through the opening and shook hands. The breakthrough became one of the defining images of modern engineering. Even more astonishing was the accuracy. After excavating almost 40 kilometers from opposite directions, the alignment error measured less than half a meter. Television networks around the world broadcast the achievement live, celebrating what many called the triumph of mathematics, engineering, and international cooperation. But despite the emotional breakthrough, the project was still far from complete. Nearly 2 more years of work remained before a single train could pass through the tunnel. Connecting the tunnels was only the beginning. Engineers still had to transform a giant hole beneath the sea into one of the safest transportation systems ever built. Tracks had to be installed across the entire route. Electrical systems, communications networks, lighting, drainage, and ventilation all had to operate flawlessly around the clock. The service tunnel became the heart of the entire complex. Cross passages were constructed every 375 meters, allowing passengers and workers to move safely between tunnels during emergencies. Massive fire-resistant doors were installed throughout the system, while powerful pumps continuously removed groundwater that slowly seeped through the surrounding rock. Ventilation systems ensured fresh air flowed through the tunnel while remaining capable of extracting smoke during a fire. The importance of these safety features became clear in 1996 when a fire broke out aboard a freight shuttle. Temperatures inside parts of the tunnel climbed to nearly 1,000 degrees Celsius. Although sections of the tunnel suffered severe damage, the emergency systems worked exactly as designed. The fire was contained, passengers were evacuated safely, and the tunnel survived one of its greatest real-world tests. It proved that the engineers had prepared for far more than ordinary train travel.
Most people associate the Channel Tunnel with the high-speed Eurostar passenger trains, but those trains represent only part of its operation. One of the tunnel's most remarkable innovations is its vehicle shuttle service. Instead of driving across the sea on ferries, cars, buses, and heavy trucks simply drive directly onto specially designed trains. Once loaded, the trains transport entire highways beneath the English Channel at speeds approaching 100 kilometers per hour. Some shuttle trains stretch nearly 800 meters long. Inside them, hundreds of vehicles remain loaded while passengers stay with their cars during the journey. From an engineering perspective, this created an entirely new safety challenge. If a fire or major emergency occurred inside one of these enormous trains, evacuating hundreds of people trapped underground would be incredibly difficult. To solve the problem, engineers designed each shuttle with sections that can be quickly separated during emergencies. Special evacuation doors allow passengers to leave the train and enter the protected service tunnel, where they can safely reach emergency exits. It was another example of how nearly every feature inside the Channel Tunnel was designed with safety as the highest priority. Yet despite overcoming extraordinary engineering challenges, one unexpected...
When the Channel Tunnel finally opened, engineers believed the hardest challenges were behind them. They were wrong. The biggest problem wasn't mechanical failure, structural damage, or even fire. It was illegal migration. Thousands of migrants and refugees arriving in northern France saw the tunnel as the fastest route to the United Kingdom. Many attempted to hide inside freight trains, climb onto shuttle vehicles, or even walk through restricted service areas beneath the channel. Some risked everything by climbing onto moving trains, unaware that the overhead electrical system carried enough voltage to kill instantly. Others became lost inside restricted zones or suffered fatal injuries while trying to reach Britain. The situation quickly became one of the tunnel's greatest security challenges. In response, authorities transformed the French terminal near Calais into one of Europe's most heavily protected transportation facilities. Kilometers of high-security fencing, motion sensors, thermal cameras, surveillance systems, and constant patrols were installed to stop unauthorized access. The tunnel operator invested hundreds of millions of dollars in advanced security technology. Even today, protecting the Channel Tunnel remains an ongoing challenge, proving that sometimes the greatest obstacles have nothing to do with engineering.
Most passengers only experience a quick train ride beneath the English Channel. What they never see is the enormous underground infrastructure quietly operating behind the scenes. The Channel Tunnel functions like a hidden underground city. Every day, groundwater slowly seeps through tiny cracks in the surrounding rock. Even during dry seasons, tens of thousands of liters of water enter the tunnel every single day. To handle it, drainage channels collect the water and direct it into massive reservoirs. Powerful pumping stations then return it safely back to the sea, operating around the clock without interruption. Ventilation is equally impressive. Because the tunnel stretches for more than 50 kilometers, natural airflow is nowhere near enough. Giant ventilation systems constantly circulate fresh air while remaining capable of extracting smoke within minutes if a fire ever breaks out. Electricity is supplied through two completely independent power networks, one connected to Britain and the other to France. If one system fails, the other immediately takes over without interrupting train operations. Every electrical circuit, communication line, and control system is backed up with multiple layers of redundancy. From a central control room, operators monitor thousands of sensors every second, ensuring that every train, pump, fan, and safety system functions perfectly. Passengers may only see a train ride. Engineers see one of the most sophisticated underground transportation systems ever created.
When the Channel Tunnel officially opened in May 1994, it instantly became one of the world's greatest engineering achievements. But financially, the story looked very different. Construction costs had exploded far beyond the original estimates, reaching roughly $15 billion, making it one of the most expensive infrastructure projects ever built. Private investors expected strong profits. Instead, they faced years of financial losses. Passenger numbers grew much more slowly than expected, while low-cost airlines and ferry operators continued attracting millions of travelers with cheaper fares. At the same time, strict agreements between the British and French governments limited how aggressively the tunnel operator could adjust ticket prices. Revenue struggled to keep up with the enormous debt. Eventually, the company accumulated more than £9 billion in debt, forcing a massive financial restructuring in 2007. The business survived and eventually became profitable. However, many of the original investors never recovered the money they had poured into the project. The Channel Tunnel became a fascinating example of how an engineering masterpiece doesn't always guarantee financial success.
Today, the Channel Tunnel is far more than a railway connection. It has become a symbol of cooperation between nations and one of the defining engineering achievements of the modern world. But engineers are already thinking about what comes next. Some proposals suggest building a second tunnel to increase capacity and reduce congestion as rail traffic continues to grow. Others imagine using the underground corridor to carry additional high-voltage electrical cables between Britain and mainland Europe, improving energy security for both regions. There are also discussions about expanding fiber optic communication networks through the tunnel, creating even faster digital connections across the continent. Looking further into the future, some experts have even proposed adapting similar routes for next-generation vacuum transportation systems capable of traveling at extraordinary speeds. Most of these ideas remain concepts for now, yet the original Channel Tunnel proves one important lesson. Projects once considered impossible can eventually become reality when technology, determination, and cooperation come together.
For more than 2 centuries, the Channel Tunnel existed only as an ambitious dream. Political conflicts delayed it, financial uncertainty threatened to destroy it, and the unforgiving forces of nature challenged every stage of its construction. Yet none of those obstacles proved stronger than human determination. Today, millions of passengers and countless tons of freight travel beneath the English Channel every year without giving much thought to what lies beneath them. Hidden below the seabed is one of the most complex engineering systems ever created, a network of tunnels, pumps, ventilation systems, safety equipment, and precision technology that has been operating around the clock for decades. The Channel Tunnel is far more than a transportation link. It represents what can happen when nations cooperate, engineers refuse to accept limitations, and innovation overcomes problems once considered impossible.
What was once called an unrealistic fantasy is now an essential connection between Britain and mainland Europe, serving millions of people every year.
The next time you see a Eurostar train disappear beneath the English Channel, remember that beneath its wheels lies over 50 kilometers of tunnels built under immense pressure with extraordinary precision and at the cost of billions of dollars and years of relentless effort. Every successful journey through the tunnel is a reminder that some of humanity's greatest achievements begin with ideas that once seemed impossible. The Channel Tunnel stands as a lasting symbol of courage, innovation, and the determination to connect people across even the greatest natural barriers. If you enjoyed discovering the incredible story behind one of the world's greatest engineering marvels, be sure to subscribe and turn on notifications. We explore the hidden science, massive machines, and unbelievable engineering projects that shape our world, one extraordinary story at a time. Thanks for watching, and we'll see you in the next video.